All right, let's get right into it. Today, we are cracking the code on a type of math problem that, let's be honest, can be a total headache. But I'm going to show you an amazing shortcut, a math hack, that's going to turn a long, boring process into something, well, kind of fun. You know this feeling, right? You see a problem like this, polynomial long division, and you just groan. It's messy, it takes forever, and there are like a million tiny places to make one little mistake and throw the whole thing off. This is the villain of our story today. And you're totally right to think that, because there is. The coolest thing about math is that there's almost always a smarter, more elegant way to get to the answer. So let's go find it.
Now, before we get to the amazing shortcut, we need to do a super quick review of why the long way even works. And it all goes back to something you learned a long time ago.
Look at this. It's the exact same structure. On the left, you've got basic division from grade school. The number you start with equals the divisor times the answer plus whatever's left over. And on the right, it's the same pattern, just with fancy-looking polynomials. This one identity right here, this is the secret key to everything we're about to do.
So this gets you thinking, what if all you needed was the remainder? Is there a way to find just that one little piece of information without having to go through the entire division problem?
We're going to zoom in on a special case. When we're dividing by something simple like x minus 3 or x plus 7, just x minus some number. This is where the magic really starts to happen. Okay, this picture shows the whole trick. Look at that formula. What would happen if we picked a really clever value for x? What if we plugged in the number a for x? Well, that x minus a part becomes a minus a, which is 0. And 0 times the quotient is just 0. That whole middle chunk of the equation just vanishes, and look what's left. The remainder is just what you get when you plug a into the function.
And that, my friends, is the remainder theorem. It basically says if you want to know the remainder, don't bother dividing. Just take the number from your divisor, plug it into the polynomial, and the answer you get is the remainder. It's that simple.
I mean, just look at the difference here. On the left, you've got that whole long division setup. On the right, you just plug in 3 and do some simple arithmetic. Both get you the same answer, a remainder of 2, but one of them is so much faster. It's not even a contest. Okay, that was pretty cool, right? But believe it or not, that was just the warm-up. Now we get to the main event, because this little trick leads to something way more powerful.
So think about it for a second. With regular numbers, if you divide 20 by 5 and the remainder is 0, what does that tell you? It tells you that 5 goes in perfectly, that 5 is a factor of 20. And it's the exact same idea with polynomials.
This is the big idea. This is the whole game changer. If you plug a number c into a polynomial and you get 0, you have just found a factor of that polynomial. It's x minus c. No division required.
And here it is formally. It's called the Factor Theorem. And see that little phrase, if and only if? That's super important. It means this is a two-way street. If you know a factor, you know a root. And if you find a root, you know a factor. They are locked together.
So what this theorem really does for us is build a bridge. It creates a direct connection between finding the roots of an equation and finding the factors of a polynomial. And this is why it's the ultimate shortcut. It completely changes the problem. Instead of trying to do the hard work of factoring, we can just do the easier work of trying to find a number that makes the whole thing equal 0. They're two sides of the exact same coin. All right, enough talk. Let's put all of this together and use our new hack to solve a cubic equation that honestly would be a real pain to do any other way. Here's our target, a third-degree polynomial. Staring at it, you might not know where to even begin. But now we have a plan. So where do we start looking for a root? Well, a really useful trick is to test the numbers that divide evenly into the last term, the 24. Let's just try some easy ones. Let's plug in 1. Nope, not 0. Okay, let's try -1. Nope, still not 0. How about let's try -2 and bingo, we got it. It equals 0. Yes, we found one. The factor theorem tells us right away that since f of -2 is 0, then x minus -2, which is just x plus 2, has to be a factor. We just found our first piece of the puzzle. We cracked the code.
Now that we know a factor, we need to divide it out. And instead of that messy long division, we're going to use its fast, clean cousin, synthetic division. All you do is write down the coefficients and then follow a simple rhythm. Bring a number down, multiply, add. Repeat. It's so much faster.
And here's what it looks like when we're done. Check out that last number on the right, 0.
That's our remainder, which proves we were right. But the real prize is what's left over on that bottom row. 1, -7, and 12. Those are the coefficients of the polynomial that's left. So what we've successfully done is taken our big, complicated cubic problem and broken it down into two simpler pieces, the factor we found, x plus 2, and this much easier quadratic. And we all know what to do with the quadratic.
That x squared part is easy to factor. We just need two numbers that multiply to 12 and add to -7, which are -3 and -4. And there you have it. The puzzle is completely solved. Our original polynomial is just x plus 2, x minus 3, x minus 4, which means the roots are -2, 3, and 4. We're done. So we went from a really intimidating problem to a simple, elegant solution, all thanks to this amazing connection between a polynomial's roots and its factors. It really makes you wonder, doesn't it? What other awesome shortcuts like this are just hiding there in plain sight, waiting to be found?